ever pondered over how transformers comprehend the position of words? It's a fascinating puzzle, isn't it? When we speak of transformers, we're dealing with models that traditionally add a separate position label to each word. To illustrate, consider the sentence, "The quick brown fox jumps." The transformer model is aware that "the" is the first word and "fox" is the fourth. However, it doesn't inherently realize that "the" precedes "fox." The limitations of this method are clear, so how do we solve this? Enter the concept of relative positions encoded as edges in a directed acyclic graph, or DAG. In the world of computer science, a DAG is a directed graph with no directed cycles. That means it's impossible to start at any node and traverse the graph to eventually return to the same node. Output? Now, how does this apply to our sentence? Well, think of each word as a node in the graph. The connections between these nodes are edges, and each edge carries information about the relative position between the words. For instance, "the" is 2 positions before "fox." What makes this method so beneficial? First, our model can now efficiently capture relationships without needing separate position labels for each word. It's similar to the industry standard self-attention with relative position representations, but BigGraph applies this as prompt pre-processing and RAG refined. Next, it offers generalization. The model can handle sentences of varying lengths because it focuses on relative positions. For instance, 2 words before works for any sentence, regardless of its length. Then we have flexibility. This approach can be applied to more complex data structures beyond simple sequences. And finally, the focus on meaningful relationships. Studies suggest that the relative distance between words is more significant for understanding meaning than their absolute positions. So there you have it, a look into how relative positions in transformer models can be encoded using directed acyclic graphs. The benefits are clear: efficiency, generalization, flexibility, and a focus on meaningful relationships. It's a testament to the power and potential of AI and the exciting advancements it brings. Graph attention networks, GATs, novel convolution-style neural networks that operate on graph-structured data, leveraging masked self-attentional layers, allows for, implicitly, assigning different importance to different nodes within a neighborhood, while dealing with different-sized neighborhoods, and does not depend on knowing the entire graph structure up front.